Hi, this is Greg Monty. I'm the director for the Center for Energy Research and Technology at NCA&T State University, and this is part of the CERT educational series on the topic of energy generation. You should have had a homework assignment where you went out and each of you on a student team explored one of 5 different types of energy generation and brought that information back to your teams and had a brief discussion to summarize what each of you found on a spreadsheet that was used. Let's see what it looked like. It was like this. It was on a file called the Energy Generation Research Summary Sheet. So you should have come back with your homework assignment completed and filled out this form together as a team. And what I'm going to do now is walk through and give you a little bit of additional information. It should be supporting what you found in your research, and this is going to be a lesson about energy generation. So there were 2 different types of sources for energy: non-renewable sources that cannot be replaced for millions of years and they're limited. And then there are renewable sources that rely on natural sources of sunlight, heat from the core of the earth, or weather, and they are unlimited. So the non-renewable resources are things like the fossil fuels of coal, natural gas, and oil, as well as nuclear. Remember, these are limited. It takes millions of years to form these different types of resources. The renewable resources are solar, wind, hydro, geothermal, and biomass. So we can replace these quickly, and usually they rely on the sun. So U.S. energy generation can be split up in the following way. You can see, starting from the top, about 20% of the U.S. is fueled by nuclear power. Natural gas is 34% and coal is 30%. The important point here is that natural gas has surpassed coal for the first time in many, many years. Just 3 years ago, it became a bigger resource for energy in the United States. Coal used to be over 50%. Non-biomass renewables only represent 13% right now. Biomass is even smaller. And this blue stuff is really wind, solar, and hydro. The electricity end user sectors are shown here. It's pretty much a 1/4, 1/4, 1/4, 1/4, with commercial, industrial, transportation, and residential sharing the load of the energy that's generated in the United States. In North Carolina, you see a slightly different situation. The U.S. showed 20% for nuclear. The state of North Carolina is at about 32% today, or at least in 2014 it was. Natural gas was about 22%, 22.5%, whereas the U.S. was 34%, and then coal 38%, and the U.S. at 30%. So we deviate slightly from the U.S. North Carolina's renewables only represented 4.5%, whereas the U.S. was 13%. So we differ a little bit from the U.S. distribution for energy generation. This next slide talks a little bit about cost of energy, and this is a really important point to take away. It turns out that the cost of things like renewables are dropping rapidly, and that's why we're seeing a big rise in the amount of wind and solar that's being installed. If you look to the far right of this chart, you see that nuclear is one of the most expensive ways to generate electricity, coming in around 13 cents per kilowatt hour. A typical bill in North Carolina is in the range of 10 to 12 cents per kilowatt hour. Coal with carbon capture is very widely varying, and it ranges anywhere from 10 cents a kilowatt hour up to 18. And actually, these numbers are probably on the low side because no plant has yet been built that actually operates and captures the carbon being generated from coal burning. Biomass is relatively expensive, around 10 cents a kilowatt hour. Coal has a wide range, again, from about 7 to 15 cents a kilowatt hour. And then you get down to the very cheapest ways to generate electricity in the United States is now solar PV at 6 cents a kilowatt hour. Natural gas combined cycle is in the same range, and wind power shows a range from about 3 cents to 8 cents a kilowatt hour. It actually turns out that these numbers are relatively old. This was in 2014. The cost of solar PV has dropped all the way down to 4 cents a kilowatt hour, and wind can be purchased in the United States in some places for as low as 2 cents a kilowatt hour. So it turns out that the energy from wind and solar is really, really low compared to all the other forms. And this is why we're going to see a continually and rapidly changing landscape for energy generation. And the last point here is this red circle with the green energy efficiency area. It turns out the very best way and the cheapest way to reduce cost is to just use less energy. So if we have more energy efficient homes, we basically reduce our cost. So let's go through the different types of generators. Let's start with coal. The process for generating electricity is pretty much the same for most of the different types of energy sources. In this case, you burn some coal, that boils water, produces high pressure steam, which turns a turbine, and that creates electricity. It's about 30% in the US for coal. The positive aspects is it's very cost efficient. It's an abundant resource. We have lots of coal across the US. It's easy to increase and decrease the supply based on demand. You simply shovel more coal into a furnace and you generate more heat and turn the turbine more quickly. The negative aspects of coal are, as we've all heard, it has a high carbon emission. Its byproduct is coal ash, which has hazardous metals and other compounds, particularly carcinogenic compounds. It's non-renewable, and it has a very high water use for cooling, and we'll talk more about that later. And this is what a coal-fired power station might look like. It's essentially got a coal coming into a furnace and being burned. It's heating water in a pipe, which produces steam, and that steam turns this turbine. The turbine is connected to a motor, and that motor generates electricity and goes out onto the power grid. So that's shown in a block diagram over here. It looks very similar for most of the different sources. You have fuel and water going into a boiler, producing steam, and it turns the steam turbine, which turns a generator, or essentially a motor, which produces electricity. And extra steam and hot water that comes off gets cooled and has come back into the facility. So that's typical coal-fired power station. Natural gas is not much different. You burn natural gas, it produces steam, it turns a turbine and generates electricity. It's surpassed coal and is now 34% of the power in the US. The positive aspects of natural gas are that it's a major source of energy. It produces 40% the amount of carbon when burned compared to coal. But this number is a little bit misleading because natural gas happens to have plenty of leaks along the pipeline, and those leaks are releasing lots of carbon into the atmosphere. So some people have actually argued that natural gas and coal are about the same when it comes to carbon emissions. The negative aspects, it emits carbon and nitrogen. It's non-renewable. As soon as we use up the gas, it'll be gone. And then the leaks from the natural gas wells are an issue today. Again, it's very similar. You have a heat source because you're burning gas. It makes the water steam, produces high pressure steam, which turns the turbine and goes through a generator and goes out onto the grid and into our homes. You have to have a big cooling tank as well to cool the turbines here because the turbines get very, very hot. And this is a problem with all of the fossil fuel generation. They all require a lot of cooling. Natural gas, coal, and nuclear require a lot of water, which comes from our streams and lakes. Nuclear. Nuclear is basically a uranium isotope. which it fissions and splits and releases heat in a chain reaction. That produces steam. It also spins turbines and generates electricity, representing about 20% of the energy in the United States today. Produces near zero greenhouse gas emissions because it doesn't burn like coal and natural gas, but there is terrible radioactive waste, nuclear accidents, and high uses of water to cool the turbines. And again, it's non-renewable. Once you've used up all the nuclear isotopes, then they will be gone, and that will be it for nuclear generation. Here's all the cooling tanks that are needed to handle the turbine heat, and it's again very similar to the other types of systems. You have a reactor with control rods which get very, very hot. It produces very hot water and produces steam. That steam runs and turns this turbine, which turns a generator and produces electricity that goes out onto the grid. And then you have all these cooling towers and a big lake or reservoir next to these cooling towers, which is constantly going through and trying to cool the turbines, which get very hot as they're spinning at very high speeds. Wind generation is somewhat different. How do we get wind and produce electricity? Well, we have uneven heating of the earth due to the sun and weather, which produces wind. You have high and low pressure systems, and then the wind turns the turbine blades up on the top of these big turbines that you see out in the middle of the fields, and then that produces electricity, which goes out onto the grid. The percentage of energy today in the United States that's generated from wind is relatively small at 4%, but it's growing very, very rapidly. In fact, almost all the new generation that's put in place in the U.S. is renewables, such as wind and solar today. There's very little going in the way of coal, and there's virtually no nuclear being added. There is natural gas, however. Positive aspects, no air pollution, and it's renewable. Negative aspects, wind farms only run when the wind velocity is high, which means that certain places in the United States are more likely to have wind turbines than others. And then wildlife, such as birds, get hit by the blades, which is certainly not good for the bird population. So this is a typical wind turbine farm with the turbines spread apart. The wind causes these rotor blades to spin, which again turns a gearbox, which turns a generator. The generator's wires then come down and go out through a transformer onto the power grid. And that's how we get electricity from wind. Solar is a little bit different. In terms of generation, the radiation from the sun hits a solar panel or a photovoltaic panel. That produces DC current, and then an inverter device converts that DC current into AC current, which goes out onto the grid. Our electricity grid is all AC current, alternating current. So the percentage of total energy generated in the U.S. is only around 1% of the total energy needs, but again, it's growing very, very rapidly, and some places like California are shooting to have somewhere in the 50% range of solar once they reach their maximum capacity for solar. The positive aspects, again, there's no air pollution, and it's renewable because it's based on radiation from the sun. The negative aspects are that it requires a large area of land, and it's viable only if the sun is shining during the daytime. So it's what's called intermittent. This is the same problem with wind. If the wind isn't blowing, the blades don't spin. If the sun is not shining, then solar panels don't generate electricity. So it's a daytime energy generator and not used at night. So there's a typical looking solar panel that's been mounted on a bunch of hardware, and you can see the system here. The key elements here are the inverter and potentially a battery. The solar cells are these small parts of the solar module. A solar module is made up of many, many solar cells. You take these modules and you build solar panels by putting multiple modules together, and then those modules go into a big solar array on a farm. And all these different devices are important. but the inverter is what converts the DC current into AC current, and the batteries are necessary to store as much energy as you can while the sun is shining, so it can be used in the evenings when the sun goes down and the panels are not generating electricity any further. Hydroelectric power is caused by the weather as well. It comes from either rain or snow that's melting, that fills the reservoirs. And then those reservoirs, which are held back by dams, those dams have big turbines in them, and the water flows through those turbines as they release the water from the lakes behind the dam wall, and that produces the electricity. The total generation in the United States is around 10%, and it's the cheapest way to generate electricity, has no air pollution, and it's renewable. The negative aspects are that it alters the water patterns with dams, and it's not a source in all states because not all states have enough topography to put a big lake up, a few thousand feet up above a lower level, which is how much you need to sort of generate the height of water that's good for running turbines. So you see a typical example here. Here's a reservoir with a dam, and that water comes down through a control gate and goes and spins this turbine. The turbine then turns a transformer or a motor, and that electricity comes out of that powerhouse and goes out to the power lines. And then that water is actually flowing from a reservoir up here down to a lower lake or a lower reservoir down below the turbines. Hydroelectric power can also be used for storing or making a battery out of it. And what they do is when the electricity is inexpensive, they use pumps to pump the water from the lower reservoir up into the upper reservoir. And then when electricity is very, very expensive, they run the water back down into the lower lake. So they shift water up during low cost for electricity and let it run through the turbines and generate electricity when electricity costs are higher. And this is called pumped hydro. And it improves the efficiency of a hydroelectric power plant by about 20%. Biomass represents the burning of grown plant materials. So you grow these biomass materials. You can produce liquid or solid fuels from those, and then the biomass is heated or burned. Again, that turns a turbine and produces electricity. Generally, what we see is about 11% of the total energy in the U.S. is produced from biomass. It's a renewable source because you can continue to grow biomass in a short period of time, a relatively short period of time. It doesn't produce air pollution, but it does use water because water is needed to grow anything in a field. So the sunlight strikes these plants, and the carbon and oxygen cycles are taking place. That plant grows, and then those plants are burned essentially to produce the heat to turn a turbine to produce electricity. Geothermal comes from the Earth's core temperature from radioactive decay. So as the Earth's core is very, very hot, that heat can be pulled up to the Earth and heat up water, which can be turned into steam, which again turns a turbine and produces electricity. It's a very small percentage of electricity is produced by geothermal in the United States. The positive aspects of geothermal are that it's continual heat production, there's no environmental damage, and it produces no emissions. The negative aspects are that it's very expensive and is only used in a few isolated regions on the Earth. You have to have a very hot region below the surface that's relatively easy to mine down to get to the hot core temperatures. And that's not available everywhere on the Earth. So this is a typical geothermal generation plant. You have a solid inner core of the Earth, and that heat is sort of radiating out to the outer core of the Earth. And so you have to drill a hole and run fluids through this hot section of the Earth down here, and it runs up and goes into a power plant producing water vapor, which turns a turbine again and causes electricity to be produced and goes out onto the power lines. So you can see that the geothermal fluid comes in here, and that produces the steam, which turns the turbine and produces the electricity. So this little box is housed in this power plant section here. Petroleum is another version of energy. Of course, we use this in our cars all the time. Petroleum is not used very much for producing electrical energy in the United States. And again, it's formed underground from decaying animal and plant materials, which turns into oil. And then it's burned under pressure, which heats water, creates some steam, and turns a turbine and generates electricity. Again, it's very similar for all fossil fuels. It produces less than 1% of the electricity needs for the United States, but is a major source for transportation. As we all know, we use gasoline or petroleum in our vehicles. The positive aspects are that it's very easy to transport, it's easy to extract, it's low cost, and it has a very high energy content in the liquid fuel. The negative aspects, as we all know, are that the resources are limited. They're predicting that there are really only hundreds of years left of oil on this earth. It produces hazardous substances as byproducts of the combustion. It has a very high carbon emissions, and it's non-renewable. And carbon emissions are important because there's a concern that too much carbon in the atmosphere is actually causing our planet to warm up and may be the source of climate change. So this is a typical look at the crude oil and natural gas pool. You see shale and sandstone down below, and a water table. Above that is the oil, which floats on top of the water, and above that is gas, which is lighter than both water and oil. And this is a typical look of the resources down in our earth. So they drill oil wells to pull out the oil. They drill gas wells, and this is also done using fracking because they can come in horizontally now into these gas layers and pull out the gas materials for natural gas burning. And this is a typical structure of the earth underneath the surface. So energy storage is also important. As I mentioned, for both wind and for solar, it's important to store some of the energy when the wind is blowing or when the sun is shining. So intermittent energy sources are not continuously available. So solar generation is only available when it's sunny, wind is only available when the wind is blowing, and then energy storage can be used to deal with that intermittency. So you can use either battery storage or pumped hydro. There are a number of other different types of storage mechanisms being explored in the United States and around the world today. But the solution to energy storage will be the key for allowing us to go completely to renewable sources of power. Battery storage is one of them. The energy generation process is to store energy in a chemical form in a battery and then convert that stored chemical energy into electrical energy. And this is what you see in all your cell phones. You have a battery in there and it produces the power to run your cell phone. And then it has to be recharged through a charging mechanism. And the percentage of the total energy generated in the United States that comes from battery storage is about 6%. The good aspects of this is it helps to balance out the grid power, and it stores energy from intermittent sources of solar and wind for later use. The negative aspects is that it can only store a certain amount of energy, and it's not all of the energy over a period of time. And it's relatively expensive today, but they're searching for less expensive ways to store energy, especially with batteries. And we've seen the cost of batteries come down rapidly, which has basically allowed electric vehicles to come into being. So what you see in large storage locations are these very large, almost train car-sized battery storage mechanisms, and then they can be used to fuel and balance out the grid from solar and wind. Here's a typical solar panel. It has some kind of a controller, and then another controller that charges or discharges the battery. So if you're producing more electricity in your solar panels than this house needs, it will pump that energy into the batteries, and then when the sun sets and the house begins to need more energy than the solar panels are producing, you can pull this power back out of the battery and into the home. Any excess power can also be driven out to the energy grid and sent to other places. I talked about pumped hydro. It's the situation where you pump water up a hill to a higher reservoir when the cost of electricity is low, and then release the water from the reservoir when the cost of electricity is higher, and that turns the turbine and produces electricity which can be sold. The percentage of total pumped hydro in the United States today is about 2%. It's cost efficient, it provides energy balancing, it's stable, and its storage capacity and ancillary grid service benefits are fantastic. The initial capital costs are relatively high. You have to put in pumps to move the water up from one lower reservoir to a higher reservoir, and it has some negative environmental and ecological impacts because you have to have dams and reservoirs which can consume large areas of land that had been prior used just for lakes or for streams. So once you build a dam, it floods everything upstream of the dam. So this is the pumped hydro. We talked about it before. You have a lower reservoir. You pump the water up to the higher reservoir when energy costs are low, and then you let it run back down through this turbine and to generate electricity in the time periods when the electricity costs are high. And last, energy efficiency, as I mentioned, is the cheapest way to save money with energy. It reduces the demand for energy if we have highly energy efficient buildings, and we have energy efficient cars, and we have energy efficient refrigerators and HVAC systems and washers and dryers. So anytime when we're using less energy through efficiency measures reduces the cost and the environmental impact. You need fewer power plants to be built, and you have much lower carbon emissions if we're more energy efficient. So the changing energy generation profiles that we see today, if you think about the Paris Accord, which concerns itself with climate change, it simulates a shift to more and more renewable sources. So you can see coal, nuclear, and natural gas use coming down across the globe, and the use of both wind and solar particularly rising dramatically. The way this can be stimulated is through the use of carbon taxes, and you're going to see that when you play the generate game. If you impose a carbon tax, you're essentially saying that those kinds of energy generation that produced carbon that goes into the atmosphere have a negative impact on the health and the operation of the earth and everyone who lives here. So the true cost of energy generation is not just the cost of generating electricity, but it's also the cost to our health. If our health is bad, we have to spend a lot more money on health care, and that adds essentially to the cost of energy generation. So there's a thought that if you can put a carbon tax on different kinds of generation, such as natural gas and coal, then you'll have a true cost of energy which is higher than what the cost is represented today by the kilowatt hours that they charge. So carbon emissions costs to society are seen in reactions to storms, rising seas, so you have many weather effects, and then you have negative health effects from the emissions. And it's not just carbon, it's noxious other fumes that are released into the atmosphere, which are also causing big health problems across the world. So I appreciate your listening. I hope that re-emphasized some of the things that you found out in doing your own research and summarized on your summary sheet. This is the end of the class 1, and the next class you're going to take, the next video, will walk you through playing the game called Generate. Thank you very much.